A brine solution of salt flows at a constant rate of 9 liters per minute into a large tank that initially held 100 liters of brine, in which was dissolved 2.2 kilogram of salt. The solution in the tank is kept well stirred and flows out of the tank at the same rate. If the concentration of salt in the brine entering the tank is 0.02 kilogram per liter, determine the mass of the salt in tank after T minutes, and then when will the concentration of salt in the tank reach 0.01 kilogram per liter. So the first thing we have to find is the mass of the salt, determine the mass of the salt in the tank. So let x of t be the mass of the salt in tank after T minutes. So with the parenthesis T is just to indicate that the mass of the salt will depend on what the time is. So once we do the calculation, we will drop this T, and you can just think of X being the mass of the salt in tank after T minutes. Okay, so since we are interested in the mass of the salt, what we will do is we will first change the rates. Thus, for example, the rate that is given here is liters per minute. So that doesn't involve the mass of the salt. Mass of the salt is in kilograms. So we will change concentrations into mass of the salt per time, or kilogram per time. So consider the entering situation. So the inflow rate is 9 liters per minute. And also that and the entering solution contains 0.02 kilogram per liter. So if we multiply these two inflow quantities, the 9 liters per minute and times 0.02 kilogram per liter. So I've written them as this so as to illustrate that what will happen when you multiply these two. So when you multiply these two, the 9 liters per minute times the 0.02 kilogram per liter. Remember, these two are the entering quantities. So you can't multiply an entering quantity by a leaving quantity. So 9 liters per minute was the inflow rate, and they told us that the entering solution contains 0.02 kilogram per liter of salt. So the liters and liters cancel out, and the 9 times 0.02 is 0.18, and you are left with kilograms per minute. So from this, we can see that by multiplying these two quantities, we get the amount of salt per minute. So that we call as the rate of entering salt, rate of salt entering the tank, because these two quantities were the entering quantities. And now similarly, let's calculate the rate of salt leaving the tank. So we are told that the inflow rate is the same as the outflow rate. So the solution of salt enters at 9 liters per minute, and they say that the solution flows out at the same rate. So the outflow rate is also 9 liters per minute. But now they don't directly give us the concentration of the salt like they gave us for the inflow. For the inflow, they gave us that it was 0.02 kilogram per liter. For the outflow, they don't give us directly. Now we know that X is the mass of the salt. So let's say in kg. Divided by, so now the question, so the 0.02 that we had for the inflow is now we have X for the outflow, and divided by the amount of liters. So the amount of liters always stays the same, 100 liters. It initially had 100 liters, and they they tell us that it stays 100 liters. So because if it's initially 100 liters and the inflow rate is the same as the outflow rate, so it means that this quantity of 100 liters is always maintained. So it flows out at So it means that so since X is the concentration of salt at any time in the tank, so at time t, not at any time, but X is the concentration at time t. So at time t, the rate of outflow will be the concentration of salt divided by the 100 liters, because it's the contents of the tank that are flowing out, and the contents of the tank are X kilogram per 100 liters. So once again, the liters will cancel out and you will be left with 9x kilogram. So the 9 divided by 100 will be 0.09 kilogram per minute. So we have the inflow rate and the outflow rate. And so the net rate of salt flow is equal to inflow rate minus the outflow rate. So the net rate of salt flow, you can call that dx by dt. We have dx by dt is the net rate, because x is the amount of salt and t is the time. So the rate of flow of salt will be dx by dt. So the net rate is the inflow rate minus the outflow rate. So the inflow rate is 0.18. Outflow rate is 0.09x. I forgot the x in the expression over here. So see, 9 over 100 is 0.09, but then there's also an x. And the kilogram per minute is just the unit, so you don't have to write that. Okay, so basically it's a question to get x. Remember, x was the amount of salt, the mass of salt. So to get the mass of salt, you just have to find x, which means you have to solve this differential equation. And now we use the fact that this is a differential equation with an initial condition given. So we are given that the amount of, so let's go up. It initially held 100 liters of brine solution in which there was 0.02 kilogram of salt. So the amount of x at time 0, x of 0 is 0.02. So it's basically solving this differential equation, and that will give us the x. So let's see. This is a linear equation. If you bring the 0.09x on the left, you can recognize it as a linear equation. I'm bringing this quantity on the left side, so it will be added up. Let's just write it by hand. 0.9x equals 0.18. So you recognize this as a linear equation. So dx over dt plus x times a function of t equals another function of t. Remember, our general form is dy over dx plus y times a function of x equals another function of x. So in this case, x is playing the role of y and t is playing the role of x. So you can say this is linear. The integrating factor will be, so if you remember, to solve the linear equation, we first get the integrating factor. Integrating factor is e power the integral of this quantity, whatever comes normally, we have a y times the function of x here. X is playing the role of y. So x times whatever we have here. So what we have here is 0.09 and dt. Normally it's dx because it's dy by dx. So if it's dx by dt, it will be dt. And this is e to the 0.09t. The integral of 0.09 is just 0.09t. Okay, so once we have the integrating factor, we know that the solution is so it's y is equal to, in this case it will be x is equal to, because x is playing the role of y, and you have 1 over I, remember, so 1 over the integrating factor. You can go back and review the linear equations if you need to. So 1 over the integrating factor, and then times the integral of, we repeat the integrating factor, times the right hand side. So the right hand side is 0.18 plus c. And so actually this 1 over I applies to all of this. Okay, so now we get x is equal to, so by the way, we did it as a linear equation. Actually, now I'm seeing that it's also separable. This is also separable because you take the dt on the other side and you bring the 0.18 minus 09x on the left side in the denominator, and then it's a separable equation. But okay, we've already started. It is a linear, so let's keep going. So this just stays. That's outside the integral. And then the 0.18 is a constant. And then the integral of e to the 0.09t is just e to the 0.09t over 0.09. So integral is just e to the 0.09t over 0.09. And then plus c. And don't forget that this 1 over I is actually applying to all of this. Okay. So when you multiply the first two things, when you distribute the 1 over e to the 0.09t over this first thing, the e to the 0.09t and the e to the 0.09t cancel out, and you're just left with 0.18 over 0.09, which is 2. So x is equal to 2. And then the second quantity would be c divided by e to the 0.09t. Or you can write it as c e to the negative 0.09t. Okay, but since we have the initial condition, x of 0 is 0.02, So it means that x is 0.02, t is 0, e to the 0. E to the 0 is 1, so 0.02 is equal to 2 plus c. This one just goes away. And c comes out to be 0.02 minus 2 would be negative 1.98. And so x will be 2 minus 1.98 to the negative 0.09 t. So let's fill it in. 2 minus 1.98 e to the negative 0.09 t. Okay, so let's see. Where did we make an error? 2 minus 1.9, so let's go back. 0.02 kilogram. Oh, this was not, initial quantity was not 0.02, but 0.2. So for some reason, I wrote that as 0.02. So this was 0.2. Let's see if we have, okay, we have it correct here. So it was 0.2 and not 0.02. So that will change things over here. So 2 minus 0.2 is 1.8. Not 1.98, but 1.8. Okay. So then they say, when will the concentration reach, when will the concentration of salt in the tank reach 0.01 kilogram per liter? So it enters at 0.02 kilogram per liter, and okay. So the mass, let's see, we have this mass as 2 minus 1.8 e to the negative 0.09 t. Let's go back to our word screen. So the concentration of salt concentration of salt at time t is, so the amount of salt is x, and the concentration, remember we found it over here. The concentration of salt in kilogram per liter is x by 100. Let's copy this. It's x by 100 kilogram per liter. So when we substitute the value of x and drop the units, let's drop the units, x over 100 kilogram per liter. And now substitute the value of x. We have this as the value of x. Okay. So if we go in the next line, let's see. Why is it not writing it? Okay, let's leave it like that then. All right, now it fixed it. Okay, so so X100 would be this one. And we want to see when will this concentration equal 0.01. So you set this equal to 0.01. All right. So now it's basically finding T from this equation. So if we multiply both sides by 100, we get this quantity equals 100 times 0.01 will just be 1. And then if we subtract the 1 on the left side and take this one on the right side, we will get just this one on the right side. And that will be equal to 1. Yeah, we moved this quantity on the right side, so it became positive, and we subtracted 1 on the left. And now you can divide both sides by 1.8. So we get 1 divided by 1.8 is equal to this E expression. 1.8 goes away, and then you take ln of both sides, so and divide by negative 0.09. So first we take ln of 1 over 1.8, and then we divide that by negative 0.09 to get the t. So I'm getting t equals 6.53. T equals 6.53. So let's see what kind of, so this is in minutes. So let's see what rounding are they looking for. Okay, 6.53 minutes, 0.53. Okay.